Hi everyone and welcome to the first session of our Diffusion Seminar. I am Woojin Kim from IDAS Lab at Seoul National University. This seminar series is designed to introduce the foundations and recent advances in diffusion models, especially in the context of language modeling. Over the next few sessions, we'll start with the basics of diffusion models, what they are, how they work, and why they've recently gained so much attention. Then we'll move on to how diffusion has transformed the vision domain, enabling powerful applications like high-quality image generation and editing. And finally, we'll turn to our main focus, diffusion language models, how these ideas are being extended to generate and control the text. In today's session, I'll give you a broad overview. We'll start with the basics, how diffusion models function, and then discuss what makes them suitable or challenging when applied to language domain. This will set the foundation for the rest of the seminar. Okay, let's get started. Let me first give you a quick overview of what we will be covering throughout this seminar. This seminar is divided into 6 main parts. We will begin with the big picture, what we call the diffusion breakthrough. This part looks at how diffusion models differ from traditional generation methods like autoregressive models, and why they are gaining so much traction. Then we'll move into the vision domain, where diffusion has made its biggest impact so far. In that section, we'll look at how these models are used for generating images, editing, and even video synthesis. After that, we'll go under the hood and break down how diffusion models actually work. This includes the forward and backward processes, their mathematical formulation, architectures like UNet and DIT, and popular sampling methods. Once we've built up the fundamentals, we'll shift gears and apply them to language. We'll cover how diffusion models are adapted for text, the challenges of working with discrete tokens, and solutions like continuous and discrete diffusion approaches. Then we'll finally look at the current landscape, what's possible with today's diffusion language models, what their limitations are, and where active research is heading. And finally, I'll show you the full seminar schedule and how each session fits together. This seminar is designed to build a solid understanding of how diffusion models work and what components they are made of. We hope it also helps you discover how these models can be applied or adapted to support your own research. Recently, diffusion-based language models have been gaining a lot of attention in the research community. We are starting to see major companies and labs explore this direction. For example, Google's Gemini diffusion, as well as models like Mercury Coder and Seed diffusion. So the question is, why now? What makes diffusion an attractive alternative to traditional language models? I mean, what is the actual benefit of using diffusion for language generation? This section is where we'll start answering those questions by breaking down what diffusion brings to the table and why it's being seen as a promising new direction for generative language modeling. Until now, the dominant approach in language generation is autoregressive modeling, used in models like GPT or Qwen. These models generate text one token at a time, predicting the next token based on everything generated so far. As you can see in the animation here, each word is produced sequentially. And until now, this works quite well. It's proven stable and highly effective across many tests. But the question is this really the most optimal way to generate language? Does generating a sentence word by word, step by step, actually reflect how we write or revise language as humans? So here's the idea I want to raise. What if we didn't have to go one token at a time? Could we generate entire phrases or even paragraphs in a single step and still keep them coherent? That's exactly the line of thinking that leads us to the diffusion-based approaches. They open up the possibility of generating text in parallel, rather than sequentially, unlocking a very different set of capabilities. Let's take a closer look at how diffusion models differ from the traditional autoregressive models. Consider an autoregressive language model like GPT or Qwen. Given an input prompt, say, "What is your favorite food?" it starts generating text one token at a time. First, it predicts I, then love, then pineapple, and finally the pizza, each step depending on the tokens that came before. Now compare that to what happens on the right with the diffusion language model. For the same input, it generates the entire sequence I love pineapple pizza all at once in parallel. This parallel generation capability is one of the key advantages of diffusion models. It opens the door to faster decoding, better control over the entire sequence, and new possibilities in how we refine or edit text. Instead of generating one by one, diffusion models allow us to treat generation more like a holistic transformation, one that evolves an entire sequence into a coherent output. This is a quick demonstration of Mercury Coder, one of the first commercial-grade language models built using diffusion. Unlike traditional code generators, Mercury is based entirely on diffusion principles. It doesn't generate one token at a time. As you can see, the generation feels much more immediate. It outputs an entire solution or code block all at once. Here's a benchmark showing where Mercury Coder stands compared to other well-known models. As you can see, Mercury Coder Small is located further to the right, meaning it achieves significantly higher output speed, measured in tokens per second. According to this analysis, it's about 4 to 5 times faster than models like GPT, Mistral, or Cloud. This speedup is largely thanks to the power generation property of diffusion models. Now, let's take a look at another recent diffusion-based model, Gemini Diffusion. This model was introduced by Google, and it's advertised as achieving the same performance as Gemini 2.0 Flashlight, but at 5 times the speed. Here, you can see the demo interface for Gemini Diffusion. Once again, it demonstrates just how fast diffusion-based generation can be, producing responses almost instantly thanks to power decoding. As you can see on the left, Gemini Diffusion shows performance that closely matches what we get from strong autologous models. Even though the architecture is completely different, the overall accuracy across text remains comparable. But what really stands out is the sampling speed. On the right, we see that Gemini Diffusion achieves over 1,000 tokens per second, which is a significant speed up compared to conventional approaches. Altogether, Mercury Coder and Gemini Diffusion show that diffusion language models are not only theoretically interesting, they are becoming fast, competitive, and commercially viable. So far, we've looked at how diffusion is emerging as a promising approach for language generation. But before that, diffusion models had already gained massive traction in another field, computer vision. It's been a few years now since diffusion-based generation really took over the vision domain. From high-resolution image synthesis to video generation and editing, diffusion models have firmly established themselves as the state of the art. In this next section, I'll briefly walk through what deep generative models are, and how diffusion rules to dominate the vision space, and highlight some of the most impactful applications. Before we dive into diffusion itself, let's first take a step back and talk about what generative models are. Unlike discriminative models, which focus on classifying or predicting the labels, generative models are designed to learn the underlying patterns in the data, and use that to create new realistic examples. The main objective here is to train a model that approximates the true data distribution as closely as possible. In other words, we want to generate outputs that look like they came from the original data, even though they were never seen during the training process. Now let's walk through the diagram. What we ultimately want is for our model to understand the true data distribution, for instance, the full distribution of natural dog images or handwritten digits or any other domain we are interested in. But in practice, we never have direct access to the full distribution. It's too complex, too high-dimensional, and fundamentally unknown. Instead, we can only work with samples from it, like a dataset of images. We take that sample data and train a neural network to approximate the patterns it sees. Over time, the model learns to represent the sample data distribution, and eventually it can generate new examples that resemble the original data, even though it's never seen them before. So, how can we actually train a model to generate data like this? The challenge is that the real-world data, like images, audio, or text, lives in a high-dimensional and very complex space. To make things manageable, we usually start from something simple, like a standard Gaussian distribution. Then, we train the model to transform samples from this simple space into realistic outputs that match the true data distribution. But here's the problem. Learning this kind of transformation directly is extremely hard. There's a huge gap between the structure of a simple prior and the structure of complex real-world data. So going from one to the other in a single step is often unstable or ineffective. Since learning a direct transformation from a simple distribution to real-world data is so difficult, researchers have proposed a number of modeling techniques to tackle this challenge. Each of these approaches makes different assumptions and uses different strategies to approximate the data distribution. One of the earliest successful frameworks is the variation autoencoder, or VAE. It uses a probabilistic encoder to map input data into a latent space, and then a decoder to reconstruct back. The model is trained to ensure that the reconstructed data resembles the original data, while keeping the latent space well structured. Then, we have generative adversarial networks, or GANs. This is often described as a police and sieve setup, where a generator tries to produce realistic samples while a discriminator tries to detect if the output is fake. Through this competition, both networks improve until the generator outputs data that's nearly indistinguishable from real samples. Another family of models is called normalizing flows. This treats the generation process as a sequence of invertible transformations, from a simple base distribution to a complex target distribution, learning each sample in the process. And finally, we have diffusion models, the focus of this seminar. These models gradually add noise to the data and then learn to reverse the process through denoising. This iterative forward and backward setup turns out to be a powerful way to model complex distributions. We'll go deeper into the theory and implementations of these models, especially diffusion, in the upcoming sessions. Let's now zoom into the timeline of deep generative models. We began with VAEs in 2013, which introduced probabilistic latent modeling. Then came GANs in 2014, which dominated for several years with models like DCGAN and WGAN. But around 2021, we entered what many call the diffusion era, starting with the DPM, followed by DDIM and models like DALI and Imagen. Since then, diffusion models have evolved rapidly, giving rise to powerful tools like Stable Diffusion, ControlNet, and DIT. Then, what's next? That's still an open question, but the momentum behind diffusion-based generation continues to grow, expanding into both vision and language domains. One of the most common and impactful applications of diffusion models in vision is text-to-image generation. These models takes in a natural language prompt and generate a high-quality image that matches the description. Examples include Imagen by Google, Stable Diffusion by Stability AI, and DALI by OpenAI. Diffusion models have shown remarkable capabilities, not only in producing photorealistic scenes, but also in creating image-native and surreal content. Their results have surpassed those of earlier generative models like GANs and VAs in both fidelity and creativity. As you can see from these examples, whether it's a cactus with sunglasses, a fantasy city on a turtle, and an astronaut or horse, the visual quality and semantic alignments are both impressively strong. Beyond text-to-image generation, diffusion models also excel at tasks like image inpainting and reconstruction, where the goal is to restore or complete missing visual content. On the left, we see Repaint, a model that progressively denoises corrupted or masked regions. It can generate multiple diverse reconstructions from the same masked input. On the right is Palette, which tackles tasks like colorization and inpainting. Given a grayscale or occluded input, it reconstructs highly realistic outputs that closely matches the original, both in color and structure. These examples show how diffusion models can learn strong priors over natural images, allowing them to reconstruct semantically consistent results even under heavy corruption. Diffusion models have also made remarkable progress in video generation, enabling the creation of temporally coherent and visually compelling video clips from just text symbols. On the left, we see Imagen Video by Google, which generates smooth high-resolution videos. On the right is Runway's Gen series, which takes diffusion-based video generation even further towards cinematic quality, often used in creative or production settings. These advances show how diffusion models are not only powerful in static image generation, but also capable of handling the complexities of motion and time. So far, we've looked at a wide range of impressive applications, from image generation and embedding to full video synthesis powered by diffusion models. But that brings us to the natural question: how do these models actually work? In this section, we'll build a high-level intuition for how diffusion models function. We'll touch on some light mathematical concepts to aid understanding, but we will not dive deep into exact formulations just yet. We will cover these more thoroughly in later sessions. As I have mentioned earlier, learning a direct transformation from a simple prior to complex data distribution is quite difficult. The model struggles to map such a leap in one go. Then, let's assume our simple prior is just a bunch of noise. Now, trying to directly turn the noise into a high-quality image, that's incredibly hard. But notice that going the other way is much easier. If we keep adding a bit of noise to real data, we'll eventually end up with pure noise. This leads to a key insight. Instead of learning a one-shot transformation, why not add noise gradually and train the model to reverse this process, denoising it step by step. This is the core intuition behind diffusion models. The diffusion process has two parts, a forward process and a backward process. In the forward process, we gradually add noise to clean data, like this cat image, until it becomes pure noise. Then, during the backward process, the model learns to reverse this corruption. Starting from random noise, it denoises step by step, eventually reconstructing the original image. Let's say we have a cat image that we want to model to learn. In the forward process, we gradually add noise to this image step by step until it turns into complete noise. Then, in the backward process, the model is trained to reverse this, denoising it one step at a time, eventually reconstructing the original cat image. Now, let's take a closer look at the forward diffusion process. The goal here is to gradually corrupt the original data by adding a small amount of noise at each step, until it eventually becomes a pure noise. We model this as a Markov chain, where each noisy image xt only depends on the previous one xt-1. With enough noise and enough steps, this process transforms the data into a standard Gaussian distribution, denoted as qxt equals the normal Gaussian distribution. So far, we've seen how the forward process adds noise and turns data into pure Gaussian noise. Now, the question is, how do we get the data back? The reverse process needs to undo the corruption step by step, denoising at each time step to recover the original input. In theory, this involves computing the true reverse transition, qxt-1 given xt. But this is intractable in practice due to the unknown data distribution. So instead, we approximate the reverse process with a Gaussian distribution, which our model learns to predict. Now, the backward process begins from pure Gaussian noise and gradually removes the noise in a step-by-step manner. At each step, we apply a learned reverse process, where the denoising model, a neural network, predicts how to clean up the noise. This model estimates the mean mu zeta, allowing us to sample the next less noisy image, xt-1. When the model is well trained, this iterative denoising reconstructs the original image with impressive fidelity. The denoising model, for example, the neural network that predicts how to remove noise, was originally based on the UNet architecture. UNet works by compressing the image into a latent space and expanding it back, allowing the model to capture both local and global features through skip connections. Recently, inspired by the success of transformers in the language domain, researchers have proposed diffusion transformers, often known as DIT, which leverage the self-attention mechanism to better model long-range dependencies. Then, let's step on to the diffusion sampling. The core of diffusion-based generative modeling lies in its sampling process. Initially, DDPM, the denoising diffusion probabilistic models, introduced a basic yet powerful approach for sampling through a long sequence of denoising steps. Since then, many improved methods have emerged, such as DDIM and DPM solver, which enhance either the speed, the quality, or both by adjusting the sampling trajectory. We will dive deeper into how these techniques work and compare their performance in the upcoming sessions, so stay tuned. Beyond generating high-quality images, we often want controllable generation. For example, generating images with specific attributes like corgi or husky, rather than random outputs. This process is called guidance, and there are two popular approaches. The classifier guidance uses a pre-trained classifier to steer the generation toward the target label. Classifier-free guidance learns to condition and uncondition simultaneously, allowing control without needing an external classifier. We will explore the technical details and trade-off of both approaches in week 7. Now that we've covered the fundamentals of diffusion models and their impressive applications in vision, let's shift our focus to the language domain. Can diffusion models be used for language generation? Then what challenge needs to be addressed, and what potential benefits do they offer over traditional methods? Let's explore how these models are being adapted to language, and what new opportunities they open for controllable and efficient text generation. Auto-regressive models like GPT have clearly made a huge impact across many domains, and they are doing incredibly well now. So then, why should we even consider using diffusion-based language models? Let's go through a few reasons. First, diffusion models allow for parallel decoding. Unlike auto-regressive models which generate tokens one by one, diffusion models can generate multiple or even all tokens at once. This parallel nature means that they can make better use of hardware and accelerate the decoding process. Second, they offer the better controllability. Thanks to a variety of conditioning and guidance techniques, such as classifier guidance or classifier-free guidance, we can steer the generation more precisely toward desired attributes or goals. Third, diffusion models support iterative refinement. Because they revisit the entire sequence over multiple steps, they can correct earlier mistakes and produce more globally coherent outputs. This is a key advantage of our auto-regressive models, which struggle to revise previously generated tokens. And finally, diffusion models naturally incorporate bidirectional context. This means they can condition on both the left and right sides of the token during generation, making them especially suitable for tasks like infilling or structured text completion. Start with the first key strengths of diffusion-based language models, the parallel decoding. This is arguably one of the most fundamental advantages of diffusion models. As we saw earlier with examples like Mercury Coder and Gemini Diffusion, these models are able to generate full sequences in parallel rather than token by token. Unlike auto-regressive models, which generate one token at a time in a strictly left-right fashion, diffusion models can update all token positions simultaneously during each denoising step. This parallel generation not only leads to a faster inference, especially for long sequences, but also unlocks better hardware utilization, since the model can fully leverage modern GPUs or TPUs in a more efficient way. This architectural difference makes diffusion models promising candidates for scaling text generation with lower latency and higher throughput. The second major strength of diffusion-based language models is controllability. Diffusion models are particularly well suited for control generation. Thanks to their iterative refinement process, we can seamlessly inject guidance signals, for example, from classifiers or attribute models, at every generation step. This allows the entire sequence to be steered progressively toward the desired attribute, such as sentiment, topic, or syntax. What's more, diffusion models also support classifier-free guidance, which means we can steer the generation using just the model itself, without relying on an external classifier. This flexibility makes diffusion a powerful framework for controllable text generation, especially in scenarios where fine-grained or multiple attribute control is needed. The third advantage of diffusion language models is iterative refinement. Unlike auto-regressive models, which must regenerate the entire sequence from a modified token onward, diffusion models can selectively refine only the affected parts of the sentence. For example, when prompted to replace the word boring with emotional, an AI model needs to regenerate the full sequence starting from that point. But a diffusion model can focus just on the targeted token, preserving the rest of the sentence. This makes diffusion models particularly useful for tasks like text editing, error correction, controlled rewriting, or stress transfer, where localized changes are important. Final key advantage is bidirectional context. Unlike autoregressive models that generate text left-right, diffusion models leverage full attention at each step, allowing them to see both the left and right context simultaneously. This enables the model to better capture long-range dependencies and maintain coherence across the full sequence. Such bidirectional capability makes diffusion models especially effective for infilling and style transfer, where understanding the full context is essential for generating accurate and full outputs. Let's now look at why diffusion models cannot directly work on text the same way they do with images. Unlike the images, text is made of discrete tokens, not the continuous values. This means that we cannot simply add noise to text in the same way we added noise to the pixel values. For example, you can see how noise added to an image. Even as noise increases, the intermediate results are still valid images. We can still recognize the cat, albeit with distortion. But for the text, things are a bit different. Look at this. Let's say we start with the sentence, "The cat sits on the mat." This maps to token IDs like 0 for T or something. If we add noise to this, we can something like 0.5 for T.71 or blah blah. But what do this mean? They are not the valid tokens anymore. You might think, let's just round them to positive integers. But that still doesn't work. Token IDs does not follow any meaningful numerical order. For example, token ID 0 might be the, but 1 might be no. This changes drastically alter the meaning. So, unlike pixel spaces, token spaces are not continuous or interpretable under noise, and that's a fundamental challenge when applying diffusion directly to the text domain. Now that we've seen why direct diffusion on text doesn't work, the next question is, how can we deal with the discreteness of the language domain? There are two main approaches. First, we can keep the diffusion process continuous, just like in images, by mapping discrete tokens into a continuous space. This is done through embeddings or latent representations. After the denoising process, the model maps the result back to the nearest token again. This forms the basis of continuous diffusion language models. Second, we can treat the noise as a discrete transformation. For example, randomly masking or switching tokens during the forward process, and learning to denoise in the reverse direction. This is called a discrete diffusion and works entirely within the token space. These both paradigms aim to bridge the gap between discrete tokens and the continuous nature of diffusion, but they do so in very different ways. First, let's take a closer look at continuous diffusion language models. As discussed earlier, these models avoid directly adding noise to discrete tokens. Instead, they map the tokens into a continuous space and perform diffusion there. There are two main approaches within this paradigm. On the left, we have diffusion LM. It operates in embedding space. The model maps each token to its embedding vector, adds Gaussian noise in that space, and then denoises. After denoising, the output is mapped back to a token surrounding or decoding based on similarity. On the right, we see LD4LG, which takes inspiration from latent diffusion. Here, an autoencoder is trained to compress text into a compact latent space. The diffusion process is applied in this latent space, and then a decoder reconstructs this original sentence. These two approaches allow us to use powerful continuous denoising techniques while still working with discrete language data. Next is the discrete diffusion approach. Instead of adding continuous Gaussian noise, this approach redefines the noising process as a symbolic transformation in a token space, such as random masking, replacement, or shuffling the tokens. Recent diffusion models like MDLM, Dream, or LADA follow this paradigm, progressively corrupting and reconstructing the token sequences through symbolic operations rather than the continuous noise. To wrap up, let's compare the two major approaches to diffusion language models, continuous and discrete. First, consider the space in which diffusion operates. Continuous models add noise in a continuous domain like the embedding or latent space. In contrast, discrete models apply diffusion directly in the token space, without converting tokens into continuous vectors. Next, look at the noising process. Continuous models inject Gaussian noise over time. Discrete models apply symbolic corruption such as masking, shuffling, or replacing the tokens. Now, let's talk about the advantages of each. Continuous models support classifier guidance, enable fast operations in low-dimensional space, and can benefit from techniques used in image generation because it's still continuous. However, discrete models are easier to integrate with existing token-based architectures, such as in LLMs, and have a simplified training objective. Still, both have their challenges. Continuous models often suffer from the training instability, require additional encoder-decoder modules, and haven't yet scaled well to large corpora. Discrete models, on the other hand, lack differentiability in their noising process and offer only limited classifier guidance. Finally, while both approaches are actively explored, discrete diffusion models have seen broader adoption recently, thanks to their compatibility with existing NLP models and training pipelines. Now, let's take a look at the model architecture. Much like their autoregressive counterparts, diffusion language models still rely on a transformer-based architecture. However, there's one key distinction: the attention mechanism. In AR models, causal attention is used to prevent the model from looking ahead, but in diffusion models, the generation is bidirectional. That means the model needs to consider both left and right context, so the attention mask is replaced with full attention. As shown in the diffulama, the below figure, this transition involved annealing from causal to full attention during adaptation, enabling the model to perform iterative refinement across the entire sequence. In the next section, I'll briefly touch on open research problems and future directions for diffusion language models. Since this is still a relatively new and emerging approach, there's significant room for exploration, both on the theoretical and practical sides. Let's take a look at some of the key challenges and to-dos going forward. One of the long-standing challenges in diffusion language models has been limited fluency, mainly because parallel generation can disrupt the token-level coherence. However, thanks to recent advances in discrete score matching theory and improved training objectives, this issue has been significantly mitigated. As shown here, models like MDLM and SED now achieve perplexity scores on par with, or even better than autoregressive models, marking a major leap in generation quality for diffusion-based approaches. While autoregressive models have been successfully scaled to extremely large sizes, ushering in the era of large language models, diffusion language models have long faced scalability challenges. High training costs and instability meant that models larger than 1B parameters were rare until recently. However, recent efforts have begun to address these limitations. For example, LADA scaled discrete diffusion models up to 8 billion parameters, and Diffulama introduced methods to adapt large-scale autoregressive models into diffusion frameworks. Still, diffusion models beyond 10 billion parameters have yet to be developed. Continued research is needed to unlock the scalability of diffusion LLMs. To further improve the scalability, promising directions include first, adapting large LLM for diffusion via attention schedule modifications, or incorporating mixture of express architecture to reduce the training costs, or finally, exploring scalable training frameworks or memory-efficient sampling methods. Next, let's talk about the decoding speed of the diffusion models. One of the key advantages of diffusion models is parallel generation, which allows all tokens to be generated simultaneously. This gives diffusion models the potential to surpass autoregressive models in speed. However, in practice, diffusion models are not yet faster than AR models. This is mainly due to two reasons. First, they require multiple iterative steps to produce high-quality outputs, often over hundreds of steps. Also, they lack the KV caching mechanisms, meaning every generation step requires full attention computation, unlike AR models that benefit from the caching. As shown in the graphs from Diffulama and Test 2 in the below figure, reducing the number of diffusion steps can improve speed, but often at the cost of quality. To address these limitations, recent work has proposed new several methods. For example, STTT introduces the time-step distillation, which effectively reduces the number of sampling steps without sacrificing the output quality. Meanwhile, DKV cache proposes the key value caching mechanism tailored for diffusion models, which enables the partial reuse of the computation across steps. Despite this kind of advancements, there is still some substantial room for the improvement. Future directions may involve the more efficient distillation or pruning strategies, or the hardware-aware optimizations, and some hybrid architectures that combine the diffusion and autoregressive benefits. Another key limitation in diffusion language models is fixed length generation. This stems from their power generation process, which assumes all tokens are generated in a fixed size format. As a result, variable length generation becomes challenging, and for short sequences, this leads to unnecessary overhead and inefficiency. To address this, recent approaches have proposed AI-like generation within the diffusion framework. One such example is block diffusion, which divides the sequence into blocks, generating one block at a time. This strategy enables the support for arbitrary lengths while still retaining some parallelism within each block. So, using this kind of techniques, instead of choosing between fully parallel or fully autoregressive, we can interpolate between the two, combining the best of both worlds. Next is the reasoning capability of the diffusion models. While the reasoning abilities of autoregressive LLMs have been deeply explored, including the chain of thought prompting, multi-step syncing, and instruction tuning kind of methods, this line of inquiry is still in its early stages for diffusion-based models. Diffusion models typically generate in parallel or by blocks, which makes it hard to revise their thinking mid-generation, unlike autoregressive models that can condition on their own evolving outputs. This presents a key challenge. The reasoning step requires the token-level dependency, something diffusion models don't naturally capture. However, recent works have begun addressing this gap. For example, diffusion of thought proposes a multi-pass generation process to better mimic step-by-step reasoning. Meanwhile, D1 introduces a gradient-based learning scheme using per-token log prop estimation under different masking strategies. These efforts represent early but promising steps toward enabling complex reasoning in diffusion LLMs. The last is the multimodal input. So far, the autoregressive-based large language models have served as backbones for many vision language models. But when it comes to the diffusion-based language models, their adoption in multimodal settings is still in its early stages. One of the major limitations in autoregressive LLMs is that they generate the token sequentially, often requiring the modality-specific designs to accommodate image, audio, or video modalities. In contrast, diffusion language models naturally generate in parallel, making them all suited for multimodal generation, where different modalities can be processed and generated simultaneously. This kind of shared parallelism across modalities presents a compelling case for unified multimodal frameworks built on diffusion. Some of the represented works on this is the Transfusion and the LADA-V. Finally, to wrap up, there are still several other promising directions worth exploring. This includes the alignment process, where reward modeling and RRHF can be adapted to diffusion, and also the personalization to tailor outputs based on user preferences and the domain adaptation mechanisms, the fine-tuning models for fields like law or medicine. We also see the potential in decoding improvements, such as speculative decoding and merging strategies, as well as enhancing the interpretability by analyzing how updates reflect the meaning. Also, new training objectives, pruning methods for faster inference, and combining with the RH frameworks are also exciting areas to moving forward. Next, I'd like to briefly introduce a few additional topics that we hope to explore in future sessions. We'll begin by covering the basics of generative modeling, including the major approaches like autoencoders, GANs, as well as the mathematical foundations needed for understanding the diffusion models, like ELBO or something. In weeks 4 and 5, we'll take a deeper dive into the diffusion framework, discussing the training objectives, sampling methods like DDIM or DDPM, and further the scoring-based learning techniques. Then, we'll explore how diffusion is applied in the vision domain, followed by the key technical components such as guidance mechanisms and the distillation techniques. In the second half of this course, we shift our focus to diffusion language models. We'll start by introducing the continuous and latent diffusion models, and then move on to discrete and masked formulations in week 9. In the week 10, we'll compare the autoregressive and non-autoregressive approaches, along with the blockwise diffusion techniques. Next, we'll examine recent advancements in diffusion-based language models, including the scaling, reasoning, and some caching strategies. After building this foundation, we'll go deeper into core theoretical components, the score matching and energy-based models in week 12, followed by the flow matching and its comparison to diffusion in week 13. Finally, we'll wrap up with a discussion on recent research trends. If you're interested in recent research on diffusion language models, please check out our creative collection on GitHub, linked below. Thank you for listening to the whole presentation. If you have any questions or would like to discuss something further, feel free to reach out to me or our lab.